Okay, class, we're going to continue our work on section 2.6, rational functions and asymptotes. We left off graphing the function y equals 2x minus 5 all over x minus 2. And what we ended up seeing here was a hyperbola, the graph of a hyperbola, in which you see a vertical asymptote at x equals 2, because again we cannot ever divide by 0. When you plug in 2, that's what happens when you see that 2 minus 2, of course, gives you that result. Nor can you have a y value of 2. And we're going to talk a little bit more as to why that y value can't be 2, but on the example we discussed in class, the basic premise was to take a look at the exponents, both of which are 1, the numerator and denominator, and therefore the coefficients of each respective expression in the numerator and denominator. Because they were 2 and 1, we end up with a horizontal asymptote simply of just y equals 2. 2 divided by 1, of course, being 1. The next thing we're going to take a look at is the definition of vertical and horizontal asymptotes. Number 1, the line x equals a is a vertical asymptote of the graph of f if f of x approaches positive or negative infinity as x approaches a, either from the right or left. Second, the line y equals b is a horizontal asymptote of the graph of f if and only if f of x approaches b as x approaches plus or minus infinity. So essentially what we're going to go ahead and do then from here, in again looking back at the last problem, we're going to go ahead and identify first the vertical asymptote, and we're also going to do that with the second thing we see, the horizontal asymptote on the last graph, and why it takes shape as such. So we're going to go ahead and say, and I like to start with the x first, I'll say as x approaches 2. Now I'm going to say that it approaches 2 from the right. Putting a plus sign to the right of the number means that you're approaching 2 from the right. So as we approach 2 from the right, we want to think about what happens to the f of x, or the y values. So let's look at it. So we're coming in from the right, approaching 2, following the curve as you see, coming in from this direction. It looks like the y values are going down. The closer we get to the vertical asymptote x equals 2, from the right, y goes down. So negative infinity is what we'll say there. And then we say, well, gosh, what if x is approaching 2 from the left? So we put a little negative on the other side there. A little different, but 2 from the left, and that's what we note. And then we can say that f of x does what? Well, if we come in from the left, approaching 2, getting closer and closer to 2, all of a sudden the y starts going up to positive infinity, and I'll just write infinity for that. Now we also want to make a note here regarding the horizontal asymptote, and because my printout didn't come out exactly the way that I'd like, I went ahead and just rewrote f of x just below. So I'm going to put option 2 here. So I'm going to say that as x approaches infinity, f of x does what? Well, we can see technically as x goes to the right, as x gets larger and larger and larger, the y values go up. Now, they don't go up infinitely, they actually go up, approaching a value that we just said on the last example, highlighting again that y approaches 2. Technically, it'll never equal 2, but it approaches that, because we have a horizontal asymptote there. Similarly, as x goes to the left, we say that f of x approaches something, and we'll see that again here. As you go to the left on the curve, x gets smaller and smaller. Y, you can see here, as the curve progresses to the left, f of x approaches 2 again. So that helps us get a better understanding as to how the vertical and horizontal asymptotes take shape, and we use this end behavior notation to help us with that. Next thing we're going to take a look at are asymptotes of a rational function. Let f be a rational function given by f of x equals n of x, n being numerator, d denominator. So n of x over d of x. We simply have this chain of terms. Again, I had to fill that in because my printout didn't come out correctly. Where n of x and d of x have no common factors. That's important. Please highlight that. So we'll move on to the next page. We'll start taking a look then at some more details. The first thing that it says on the next page, the graph of f has a vertical asymptote at x equals a if d of a equals 0, and n of a does not equal 0. So vertical asymptote at x equals a. Again, if the denominator, however, is equal to 0. Now we know we can't ever divide by 0, but when our denominator does equal 0, we then say, well, that's got to be a vertical asymptote. Second, the graph of f has one horizontal asymptote or no horizontal asymptote, depending on the degree of n and d. Part A of 2 says that if n is less than m, in other words, if the numerator degree is less than the denominator degree, then y equals 0 is the horizontal asymptote. It's the x-axis, technically. And that's, of course, of the graph of f. B, if n is equal to m, which we saw on example 1 on the previous page, then y equals a sub n divided by b sub m is the horizontal asymptote. Next, option C. If n is greater than m, then there is no horizontal asymptote of the graph of f. One thing we will take a look at later, though, is that when n is greater than m, we don't have a horizontal, but we have a slant asymptote. You may sometimes hear me refer to a slant asymptote as an oblique asymptote, but slant asymptote should suit us just fine, definitional or I guess terminology-wise. Example 2. So find any horizontal and vertical asymptotes of the following. We've got f of x equals x plus 1 over x squared minus 1. So what I'd like to usually do with these problems, I like to start out with what n and what m happen to be. N is 1, in other words, the numerator exponent, or degree we can even say, and the denominator exponent 2. So how does n and m relate? Well, n, because it's 1, is less than m because it's 2. Because n is less than m, we know that we're talking about up above 2a, and we can pretty much right away highlight the fact that for the first and the second items, really the second item in particular, which I'll highlight first. Second item in particular, we can actually just simply say it is a. In other words, the horizontal asymptote is y equals 0. Back to the first item, in other words, what are our vertical asymptotes or asymptote? Well, we can go ahead and identify using the same premise from the previous page, setting the denominator equal to 0. Now we know that it can't equal 0, but we set it equal to 0 when defining our asymptote or asymptotes. We say that x squared equals 1. We take the square root of both sides. We end up with x equals plus or minus 1. Now before I go ahead and just say these are in fact our vertical asymptotes, I'll get ready for it though. We do need to do one other thing, and this could possibly happen depending upon the function. We need to look at our function, and we need to see if there happen to be any common factors. Because if you remember the language from the previous page, it did discuss or refer to the fact that n of x and d of x have no common factors. Well, in this case, if we were to actually take that step, following the original setup, and actually see if we have common factors, which I think you can see that we do, x squared minus 1 is factorable as x plus 1, x minus 1. So what happens here is that these two factors divide out. So the simplified version of this rational function looks like this. So what does that mean with regards to then our vertical asymptotes, when we found that our vertical asymptotes were plus or minus 1, plus or negative 1? Well, we actually don't count one of those values as a vertical asymptote, because technically what we have here is something called a hole. We have a hole when x equals negative 1. So I'm going to rule out the negative value there. Our vertical asymptote is only at x equals 1. We're going to take a look at the graph of this function. We may not look at all the graphs, but this one in particular I do think is worthwhile taking a look at. So if we go ahead and take a look, we'll go ahead and graph. So y equals, and I'm going to put parentheses, x plus 1, and that, of course, divided by parentheses, x squared minus 1. Zoom 6. Let's see what we got. So here comes our hyperbola. There's two branches. We do have a pretty obvious horizontal asymptote at y equals 0. We should also have a pretty obvious vertical asymptote at x equals 1. There is, if you were to hit second trace, option number 1, there is not a vertical asymptote at -1, but a hole. Now the hole isn't and shouldn't be defined at all, and nor should you really even see it on the graph. But it is there, and we should make a note of it in the sense that our function approaches -1 from the left. It even approaches -1 from the right, but there's a point here, technically, that is not supposed to be filled in. If you were to zoom in enough, you would actually see this as a kind of a gap on the graph. They actually call it a hole. Gap we've heard in the past in various contexts, but hole is exactly what we're talking about. So, graphically speaking, if I were to lay this all out, it would take the shape as such. So we would have, no big surprise here, we should have this as our horizontal asymptote. We see this as our vertical asymptote. So our function comes through below, of course, the horizontal asymptote. So that does this. I do want to highlight the fact, before I graph this and note what the hole is, let's highlight ordered pairwise what the hole would look like. And we're going to do that as such. We're going to go ahead and we're going to plug in -1 into the simplified version here. So if we plugged in -1, we'd have 1 over -1 minus 1, which is, of course, 1 over -2. So the ordered pair for my hole is at -1 comma -1/2, which is roughly here. Okay? So we go ahead and graph our hyperbola. It looks something like this. And again, I'm kind of roughing this out. It's not an exact graph with various points. Just to give ourselves, though, an idea as to how it takes shape, this is what we're looking for. Okay, and we can reflect back if we need to, taking a look at the graph on the calculator. And just as one last additional point here, I'll have domain and range as our last two things to find. The domain of this particular function will start off as negative infinity. It'll go to -1, the whole. It's going to be a parentheses, and that'll be in union with -1 to our vertical asymptote at 1. And then that will finish with in union with 1 to infinity. As far as the range goes, we are going to think about the left part of our curve on the bottom left corner here, noting that we can have y values as low as, we'll go with -infinity first, coming up, however, to the y coordinate here of the hole, which we know we cannot have, so I'll say -1/2, parentheses, in union with -1/2, and then we know that the horizontal asymptote is a limitation in the y direction, so I'll say to 0, parentheses, and then that will then be in union with 0 up to infinity. Now there I'm, of course, looking at the curve on the far right upper corner there, and that's going up to positive infinity. Let's move on to part B. So part B is identify all those characteristics again, but for 2x plus 5 over 4x minus 6. So we'll go ahead and do with this one, similar to the last problem, as we'll start off looking at number 1, and then, of course, number 2. Now, I do typically like to look at the denominator right away and highlight what we know we cannot have, particularly here in the denominator. We know we can't divide by 0, so I'm going to set it equal to 0. And when I solve, I end up with 4x equals 6, x equals 6/4, or 3/2. So my vertical asymptote is just x equals 3/2. There's no hole on this particular problem. We can obviously test both numerator and denominator, seeing if there's any GCF possibly, and then in turn if there's any common factors. The second thing we'll go ahead and do is we'll determine what kind of a horizontal asymptote exists, if any. And we're going to go ahead and continue that in part 2.